Okay, well, we left off on the one about the sets. So that was probably maybe like number 23. Okay, so let's go ahead and figure this out systematically. So all you have to do is write down the numbers themselves. And what? No, we didn't actually. I explained how to do it, but we didn't actually. At least maybe, well, some of you obviously did finish it. But we didn't actually enter the answers. 21, 21, 31, and then 6, 13, 14, and then okay, so I'm gonna stop sharing that window so I can actually write something down and record it. So what we know is that the three sets A union B union C have a total number of 42 things in them. That's what we know. And then we know that A itself has 21 things in it, and B itself has 21 things in it. Now, I'm doing the one that was on my homework. And C itself has 31 things in it. And then it says that the intersection of A and B has 6 things in it. The intersection of A and C has 13 things in it. And the intersection of B and C has 14 things in it. We do not know how many things are in common to the intersection of all three sets. So that's called X. But we know from the inclusion-exclusion principle that the number of things that's in A union B union C is equal to the number of things that's in A plus the number of things that's in B plus the number of things that's in C minus the number of things that's in A intersect B minus the number of things that's in A intersect C minus the number of things that's in B intersect C plus the number of things that are in A intersect B intersect C, which is what we're looking for. So I can solve this equation for the unknown amount of what's in common to A intersect B intersect C, which is X, just by doing arithmetic. So 21 plus 21 is 42, plus 31 is 63. So 42 equals 63. Minus, let's think, 6 and 14 is 20, and then 30 and then 33, so minus 33 plus X. 63 minus 33 is 30. So 42 equals 30 plus X. So in this question, it looks like X is 12. Unless I did something wrong. Well, I don't think that's possible. Hold on. Did I do the arithmetic right? 21, 21, 31, minus 6, minus 13, minus 14, and then plus X. 42 reported relief from least 1. Let me think. Did I do this right? No, I did not do that right. 21 plus 21 plus 21 plus 31 is not 63. It's actually 73. So you have to do your arithmetic right. So 73 minus 33 is actually 40. And so 73 minus 43 is actually 40. 73 minus 33 is 40. Yep. And then what do you think X equals? So 42 minus 40 is 2. So X equals 2. That means there's 2 things in common to all 3 sets, which makes all the rest of it be easy because how many people got relief from all 3 drugs? That would be 2. And based on that, it's easy to fill out the rest. Because since we know 2 people got relief from all 3 drugs, that means 2 is in the center spot. But it said 6 people got relief from drugs A and B. So that means if there's 6 people in the intersection of A and B, what is 6 minus 2? 4. So there has to be 4 people who got drugs from A and B, but they did not get drugs from A, B, and C together. And then it says 13 people got relief from drugs A and C. So these two numbers right here that are in common to A and C have to add up to 13. So what's 13 minus 2? 11. And then it said that 14 people got relief from drugs B and C together. So these two numbers are in common to B and C together. Hold on, let me stop sharing this window. My fault. Hold on, I need to share this window. These two numbers that are in common right here, they have to add up to, oh, I forgot the numbers, but you can't do everything at once. Okay, 14. They have to add up to 14. So that would be 12 right there. And then how many were in common too? You know what you really need is everybody needs 3 computers and 3 iPads all at once. Then you can see everything at once. Okay, then you would have now how many things are in A? 21, right? So that means everything within the circle A has to add up to 21. So how many things are in it already? 13 plus 4, 17. So 17 plus 4 more is 21. And then you do the same thing for B. There are 21 things in the drug B, and you have 12 plus 4, 2 is 14, plus 4 is 18. So that means that you'd have to have 3 more left in B. And the number of things that's in C is 31. So add these up. 11 plus 2 is 13, plus 12 is 25. And you have to have 31 total, so there's 6 more that are in C total. So those are the number of things that are in the whole answer. How many subjects only got relief from drug A only, but nothing else? That would be 4, right? Because there's 4 in that spot. So perfect. Okay, good job. Now, what we're going to learn in the next couple of problems is one of the most important things, but we didn't really have time to cover it very much. So pay close attention to it. This is called, either sometimes they're called multi-valued equations, or they might be called vector equations, or they are just called matrices. Matrices is the easiest word to use. It just sounds like the matrix, so it sounds scary. But here's what you have: multiple equations in the same equation, or vectors, or matrices. So A plus B is equal to -3. That's what we know. A minus C equals 0. C equals -2. And B minus A equals 1. Which of those 4 statements is a definite statement that we can tell what the answer is for sure? There's only one of them. C equals -2. So let's put C equal to -2, but we don't know what A is and we don't know what B is yet. But we do know that C is equal to -2 because that part of this multiple valued equation has a specific solution. Now that we know what C is, let's plug in what C is into this equation. This top corner on the right says A minus C, and the top corner on the right says 0. So A minus C equals 0. If you have the equation A minus C equals 0, what you can do is you can bring the negative C on the left side to the right side. So you get positive C on the right side. So then you get A equals C. So A has to equal C. What is the value of C though? -2. So A has to also equal -2. Now look at the third last equation. B minus A equals 1. B minus A equals 1. So that means that B minus -2 equals 1. That means that B plus 2 equals 1. So if B plus 2 equals 1, then what does B equal? So if you have the equation B plus 2 equals 1, can anybody tell me what B equals? If B plus 2 equals 1, -1. Yeah, because -1 plus 2 equals 1. So B equals -1. And then in order, the answers are A equals -2, comma, B equals -1, comma, C equals -2. Then we have another equation to solve. Let's solve it also from the simplest one to the most complicated. The left corner says 2A equals 4. So if you have the equation 2A equals 4, 2A equals 4, what does A have to equal? 2. So we know A equals 2. Now let's go to one that involves A somewhere else in the problem. So we know that this one says C minus A, which means C minus 2 equals -1. So if we know that C minus A equals -1, and if we know that A equals 2, that means we know that C minus 2 equals -1, and we can move the -2 to the other side and make it +2. So C equals -2 minus 1. So what is C? 1, correct. So let me backspace that line. So I know C equals 1, but I don't know B. However, I do know that B, I do know that B, let me look for it right there. The second equation, B plus C equals 5. So I know that B plus C equals 5. However, I know that C equals what? 1, right? So B plus 1 equals 5. So there's only one number plus 1 equals 5. What is that number? 4. So B has to equal 4. So therefore, I know that B equals 4. So there's that. Now, here's the last thing we're going to learn about these types of problems before we start doing binary trees. When you have a matrix times a matrix, you take everything in each row of the first one times everything in each column of the second one. And then you add together the results to get the results in each corner. So 3 times 1, so the ones that I've highlighted, they get multiplied by the row, the first row. So you do 3 times 1, which is 3, plus 0 times 0. What is 3 plus 0? 3. Correct. I'm going to leave it as 3 plus 0 at first, then I'll change it later. Then you do this first row, I'm going to keep that highlighted, times the second column. What is 3 times 1 plus 0 times 2? That's 3 plus 0 again, right? And then what is 3 and 0 times 4 and -1? That'd be 12 minus 0, right? Okay, that was good. Now, let's go to the second row of the first matrix. You do that row times each column. So you do 1 times 1, which is 1, plus -2 times 0. So you get 1 plus 0. Then the next, you do this row times the next column. So it's 1 times 1, which is 1, plus -2 times 2, which is -4. So it's 1 plus -4, which is 1 minus 4. Last but not least, we have this second row times the last column. 1 times 4 is 4, and -2 times -1 is +2. 4 plus 2. Now let's simplify those answers. What is 3 plus 0? 3. What is 3 plus 0? 3. What is 12 minus 0? 12. What is 1 plus 0? 1. What is 1 minus 4? -3. What is 4 plus 2? 6. So it's equal to 6 for the last one. Now let's go ahead and click submit. I'll submit all the other ones as well. I guess I already did that one. Okay, so now let's go to the binary tree. So this one says use the steps of algorithm 10.5.1 to build a binary search tree for the given keys. Now, this specific algorithm is probably the most basic one. It does not guarantee that your answer will be balanced. And in real life, it's critical for speed and efficiency to keep your binary trees as balanced as possible. This algorithm, the balancing of the tree depends completely on the order that the keys are given to you in the algorithm. So we're going to start with 16, and the algorithm works like this. If the number you need to insert next, which is 26, is lower, you put it on the left. If it's bigger, you put it on the right. That's basically all there is to the algorithm. It's extremely basic. So should 26 go on the left or the right of 16? Right. To the right, correct. Now you go to 25, and you always start with the root of the tree, which is the first vertex. So is 25 bigger or smaller than 16? Bigger, so go to the right. Now there's already a spot there, so you can't use that spot, so you do it again. Is 25 bigger or smaller than 26? Smaller, so go to the left. Now go to 5. Insert 5 into the tree using the same algorithm. Look at the root of the tree, and is 5 going to be to the left or the right of 16? Which one? Left or right? Left. And now go to 19. Try to insert 19. So is it bigger? Is it going to be to the left or the right of 16? To the right, because it's bigger. So now look at 26. Is 19 going to be to the left or the right of 26? To the left. Now look at 25. Is 19 going to be left or right of 25? Left. Correct. So there we go. Now 8. Is 8 going to be to the left or right of 16? Is 8 going to be to the left or the right of 5? Correct. Then 7. Is 7 going to be left or right of 16? Is 7 going to be left or right of 5? Is it going to be left or right of 8? Correct. So it ends up right there. So it's pretty easy. Probably even a like second grader could do this. But making balanced runs is a lot harder. We're not going to learn how to do that because you'd have to have a really I'm gonna give you a couple mention a couple words. There's something called splay trees. There's like red and black trees and AVL trees and all kinds of different trees that you can use. By the way, when I was a teenager, like 15 years old, I ordered a book called The Design and Analysis of Algorithms by Dexter Kozen. It went into all sorts of algorithms about trees and things like that. So I'd highly recommend if you're in computer science that you study some of those algorithms. Okay, 16, 7, 5, 25, 19, 26. Let's do it again. You always put the first one in the first available spot. So 16 goes in the top. 7. Does 7 go left or right of 16? And then 5. So 5, does it go left or right of 16? Does it go left or right of 7? Correct. Now 25. Does 25 go left or right of the root? Does 20, so now there's an open spot, so boom, it goes in the open spot, first open spot. 19, does 19 go left or right of 16? Right. Does 19 go left or right of 25? Correct. 26, does 26 go left or right of 16? Right. Does 6 go left or right of 25? Right. So there we go. Now 8. Does 8 go left or right of 16? Left of 16. Does 8 go left or right of 7? Goes to the right. Now notice this one's balanced. Everything is filled and everything only goes down to 2 levels instead of having numbers go down to 3 levels. So this tree is perfectly balanced. And we actually have the exact same numbers in both of those trees. So this is the observation of this is just to teach you that if you have the numbers in different order with this basic algorithm, it will create a different tree. If you're lucky and you have them in a certain order, you might get a balanced tree. If you don't have them in a certain order, you'll get an unbalanced tree. Or not, and maybe sometimes it could be balanced, but maybe it's very inefficient. So being fully filled and balanced makes them the most efficient. Okay, so then, by the way, it says to enter none in any unused blanks. So if I submit this answer, I'm going to show you how to get the easiest points on this whole homework assignment. Ready? So first let's submit and make sure that those are all correct. We only got 14 out of 22 points. So what do you have to do to get the other 8 points? Easiest points in the world, just put none. Except don't leave the space after the word none, though. There we go. Just put the word none in each box. Then you'll get the 8 easiest points in the whole assignment. Boom. Except you have to know where the none goes in order to get those 8 points. Okay, there we go. Sweet. Now, next one. Use Kruskall's algorithm to find a minimum spanning tree for the following. By the way, that's why you have to get a perfect score on this in order to not have to take the final. Because if I just say that you have to get an average of 90, which I said you could do that if all of you got an average of 90, but individually to not take the final, you have to get a perfect score on it. That's because some of the problems that are just as important, like this one, they're only worth 2 points. So you could easily get a 90 without doing some of the most important questions. So use Kruskall's algorithm to find a minimum spanning tree for the following graph. So I actually did this problem already to make a diagram of it and have it in my notes so I wouldn't have to go back and forth between the computer screen, but I forgot to bring that piece of paper with me. So let me draw these things again. Just a second. Okay, so boom, boom, boom. 1, 2, 3, 4, 5, 6, 7. One more. Okay, so this is V5, V0, V6, V7, V3, V1, V4, and V2. And then the edges are 12, 4, 10, 2, 7, 5, 20, 19, and 13, and 8. Okay, I should be able to do it now. Okay, so let's stop this and start this. So make sure that you remember these algorithms though. If you ever have like a quiz on discrete math, people might ask you these questions. Okay, so here is point V naught. Here over there is on the left is point V5. And then over here is point V6. And then right in the middle is point V4. Up on the top right side is point V1. Here right here is V3. None of this is Kruskall's algorithm. This is just a picture that they gave us. There's point V7, and then over here is point V2. Now, Kruskall's algorithm, I'm going to show you the picture again because you might not have written it down. It's based on the edges, and it's very simple. All you do is you write the edges in order from the shortest to the longest. So do you see that this edge has a length of 2? This blue line has a length of 2. This blue line has a length of 4. This blue line has a length of 5, and so on. So what you do when you are doing Kruskall's algorithm is you always pick the shortest edge first. So what's the shortest edge in the whole picture? It's this edge right here. I'm going to do it in red. This edge right here, because that edge had a length of 2, right? That's the shortest edge in the entire picture. So I'm going to take my regular pen and just mark that off. And the only requirement is we're trying to find the shortest possible spanning tree of this graph. The only thing is you cannot add an edge if it makes a loop. A loop is something that goes around in like a circle or anything that creates a pathway that skips some of the other points. So like if I join this edge to this edge, that would not be a loop yet. But if I join this edge to this edge, this vertex to this, and I connected it to that would make a loop. I could travel around that loop and I would never have to go to any of the other vertices. So you add the edges from shortest to largest, except if you have an edge that makes a loop, you have to skip it. So let's do that. The next shortest edge is edge number 4. So by the way, I'm going to label these in blue, the order that I did them in. So this is number 1. Now let me go back to red. We're going to connect that edge because that edge has a length of 4. And that was step 2. So look at the picture and tell me what edge comes next. What edge is the next shortest between 2 and 4? What edge is the next shortest after 2 and 4? 5, correct. So let's add edge 5. So let's add edge 5. And that's the third step. Okay, now what edge is the next shortest after 5? I'll give you a hint. We're not going to include that edge actually. But it's 7, yep. But why can't we add edge number 7 to the graph? So why can't I put edge number 7 in the graph like this? Can anybody tell me? I'll make a loop, right? So that will not make the minimum spanning tree because loops do not make the minimum spanning tree. Okay, so there we go. Because they connect things that are already connected, which makes it not the shortest possible tree. Okay, so then we're going to skip 7 because it makes a loop. So what's the next shortest after 7? It'd be edge 8. That one does not make a loop, so let's do that one. So let's do edge 8. By the way, that's not actually called edge 8. It just has a length of 8. These edges don't really have names to them. And that's the 4th step that we're doing. Okay, so then what's the next shortest after edge 8? 10. So that does not make a loop. So let's connect that one. So edge 10, and that's step 5. Then what's the next shortest after edge 10? How about edge 12? But edge 12 would make a loop though, right? If I connected edge 12, which would be along the top, that would make a circle, a circular loop. So skip edge 12. How about edge 13? Would that make a loop? Nope. So let's do edge 13. So that'd be step 6. And then we could do step number 18. But if we connected step 18, this to this, that would make a loop, right? So we're going to not do that. Instead, we're going to go to the vertex number 19 and connect that one. So that's step 7. So the order that we connected them in, the order that we connected them in was V3 to V4 first, and then V0 to V5. So we did V3 to V4 first. So put that set first. Then we did V0 to V5. So put that set second. And then we did V1 to V3. Now, by the way, it accepts it right. The order doesn't matter in this case because this graph is a non-directed graph. So saying V3 V1 is accepted. That's what I put it in as, although I later realized the computer's official answer key says V1 first and then V3. But it doesn't really matter. It still gives me credit for it. So you do V1 to V3 first, and then I forgot what came next. So after edge 5, we skipped edge 7, right? We went to edge 8. Yep, we skipped edge 7 because it would have made a loop. We skipped edge 7 because that would have made a loop from around these three sides. So we went to edge 8, which is V5 to V6. Then we went to that one, V5 to V4. And then we went to bottom V6 to V7, and then we skipped edge number 15 and edge number 18, and we went to edge number 19 as the last one because those two other edges would have made a loop. So it's very simple. You just simply add the shortest edges to the shortest to longest, but any edge that makes a loop, you skip it. That's all the Kruskal's algorithm is. So can you remember that? Okay, let me do attendance real quick. Perfect. Okay, 11:24. America, LaShawn, good job. Shamarius, Anthony, Zoe, okay, good job. Isaac, he's gone. Noah, okay. Anthony Johnson, Colin Morrison, Ignacio, Caleb, you're here, right, Caleb? Okay, good job. Arturo Taylor Logan, sir. Perfect. Marqueta, good job. Okay, there we go. Now let's go to, and then we draw the diagram. So the diagram is the same one that I drew down there. That's what it looks. Mine is more crooked though, but it's going to be that diagram right there at the end. So perfect. Now we're going to use Prim's algorithm. We already learned this one in class, but Prim's algorithm, instead of focusing on the edges, you focus on the vertices. So the difference is you can start with any vertex you want to. You can be told anything, but you can still come up with a minimum spanning tree. The reason that works is because a minimum spanning tree will always contain all the vertices. That's what it means to be a spanning tree, is that it contains all the vertices. So you could start with any vertex and still come up with a minimum spanning tree. So spanning means it contains all the vertices. In order to span a tree, it means it contains all the vertices of the graph. But a minimum spanning tree means it covers all the vertices in the shortest way possible. So Prim's algorithm basically lets us start with any vertex that we want. So we can start with the vertex V0. But then we connect it in the shortest way possible to a vertex that's not yet in the tree. That's the key, though. It has to be a vertex that's not yet in the tree. Now, we don't have to worry about loops, but theoretically, though, by always adding vertices that are not in the tree yet, it's impossible to form a loop. Why is that? Because if we only connect to vertices that are not in the tree yet, that means they have no connections around to any other points at all. So there's only going to be one link to them when we add them to the tree. So they won't be able to form a loop. So we don't have to worry about loops in this case. So start with V0. What's the shortest path from V0 to any vertex that's not yet in the tree? So we're basically starting with the tree with one point in it, V0, and then we're growing the tree by connecting it. We're linking it to one other vertex. But it has to be linked by an edge, though. There's only two edges coming out of V0, and we picked the shortest one. So what vertex is joined by the shortest edge coming out of V0? Correct. So we're now including that one right there in it. So mentally just mark that off in your mind. And then after that one, both V0 and V5 are in the tree. Now look at all the edges that come out of V0 and V5 and pick the shortest one. 12 and 10 and 8. 12, 10, and 8. Those are the only edges that come out of V0 and V5. Pick the shortest one, which would be 8, right? So that edge right there goes from V5 to V6. And before you do it, though, ask yourself, is V6 in the tree yet? No, it's not in the tree yet. So by connecting V5 to V6, you will not be joining it to any vertex that's already in the tree. So that means we can do it. Now we have three vertexes in the tree, V0, V5, and V6. Look at all the edges that come out from them, 12, 10, and 13. Pick the smallest one, which is 10, and we're going to use that one. So 10, what are these two vertices that it connects? V5 and V4. Which vertex is going to be added to the tree by that? And is V4 already in the tree? No, not yet. So go ahead and connect I think the computer will probably write it as V4, V5 because it writes it in numerical order. So go ahead and add the edge from V4 to V5. Now we have 4 vertices in the tree and find all the edges come out of those 4. So 12, 7, 13, 15, and 2, and pick the smallest one, which is going to be 2, right? So we're going to pick 2. And the vertex 2 connects to V3, and V3 is not in the tree yet. So we're going to go ahead and connect the line from V3 to V4. Boom. Oh, nuts. Oh, sorry. Hold on just a second. Forgot. This is horrible of me. I need to share this window. Okay, there we go. So there's that. V3 to V4. Okay, now what's the shortest edge that connects to something that's not in the tree yet? By the way, it gets harder it only works best if you have been drawing a picture yourself. Your mind cannot keep track of everything that you've already done without somebody to write on it. V3 to V1. Okay, that sounds good to me because V1 is not in the tree yet, right? So V3 to V1. I'm just going to go ahead and say V3 V1 because the order doesn't matter. Okay, there we go. Then, so which vertices are on the trees already? That one, that one, that one, that one, that one, and that one. There's only 2 more that are not in the tree. So what's the shortest link from something in the tree to something that's not in the tree so far? V3 to V7? V6 to V7? Okay, V6 to V7. Okay, I agree with that. And now there's only one thing not in the tree, which is V2. What's the shortest path from something that's in the tree to V2? V7, right? Yeah. So it'd be connecting from V2 to V7. That should work. And then, okay, let me just double check. Well, I guess I don't have a way to double check that. But then the drawing should go from V0 to V5 to V6 to V4 and then to V3 and then to V1 and then to V7. So it should go, so I wish I could like highlight these somehow. So it goes these lines, these lines, these lines, and then up across the bottom and up. But these two lines right here, this line, this line, this line, and this line, those are blank. So it comes along the bottom and then up and over. So I think it's that one. Does that look right? Yeah, that one looks right. Okay, let's submit it. So do you see how Kruskall's algorithm focuses on edges, whereas Prim's algorithm focuses on vertices? Perfect. Okay. So let's just go through those things one more time verbally. Kruskall's algorithm, all it does is just add the smallest edges, and then the next smallest edge, and then the next smallest edge, except it skips the edge if the edge would create a loop. If there is ever an edge that would create a loop around something without covering all the circle, without and skipping some of the points, then that edge is skipped. And then the result is a minimum spanning tree. Prim's algorithm starts with any vertex, so you don't have to start with the smallest, it starts with any point, any vertex. And then from there, it connects the shortest possible connection from that point to a point that's not yet included. And then once that point is included, then it tries again. It finds the shortest possible connection from any of those 2 points to another point that's not included yet. And then it finds the shortest connection from one of those 3 points to some other point that's not included yet. And then when you're done, it finishes. Okay, so now this one, 29. So we're getting closer and closer to the end. So I misread this problem last night. I thought this said 1 to n because it was like super small on my phone or whatever, but I kept getting it wrong, and then I realized, wait, it's actually way easier. So for I equals 1 to n minus 2, and for ij equals 1 to n. Okay, let's remember we can only do this if we start with 4. So assume n is 4 for the first case, and let's work through this together. So what would the outer loop do if you went from n equals 4? What would happen? I go for I equals what to what? Right, so I would go from 1 to 2, and then the inner loop would go for j equals 1 to what? Oh, no, not 1. That's I, my fault. I to 4, right? So basically, the outer loop would run twice. The inner loop would run, well, the inner loop would also run twice because the inner loop is within the outer loop. So, I mean, the inner loop would be run twice, but within the inner loop, it would run from I to 4. So from 1 to 2, from I to 4. So the first time the inner loop would run, it'd be from 1 to 4. And the next time the inner loop would run, it'd be 2 to 4, right? So how many numbers are there from 1 to 4? 1 to 4 equals 4 numbers. 2 to 4 equals how many numbers? 3. So you get 4 plus 3, right? Okay, so for the first case, it'd be 4 plus 3. What if n is equal to 5? Well, then the outer loop would run one more time, right? Because if we make n bigger, the outer loop runs one more time. Then the inner loop would run one more time. So it'd have another loop that would run 5 times, right? Because I would go from 1 to n, but n would be 1 bigger. So it'd run 5 times as well. So it'd be 5 plus 4 plus 3. And then if n is equal to 6, the total number of operations that would do would be 6 plus 5 plus 4 plus 3. So this almost rings a bell Do you know what numbers are missing from this? If we have the pattern 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, etc., that's almost like saying 1 plus 2 plus all those, right? So the pattern is actually the same as 1 through n, except it's missing what? It's missing the first two, right? So how big are the first two? What's 2 plus 1? So 1 plus 2 plus 3 all the way through n is equal to n times n plus 1 divided by 2, right? And then if it's missing the first 1 and 2, the beginning of it, it would take n times n plus 1 divided by 3 operations. So I don't remember if that's what I had last time, but it should work though. By the way, what if yours says for I equals 1 to n minus 3? Then how many operations would it be? I'm just going to guess it would be missing 1, 2, and 3 from the first. So it'd be 1 plus 2 plus 3 is 6. So it would probably be n times n plus 1 over 2 minus 6 in that case. But I don't know what your answers might have. Now, what order does this algorithm have? Well, it has an n times n, which is n squared. So this is an order of n squared. So submit that. Perfect. Let's see what comes next. Okay, so here's a regular expression one. So consider, let me change my answer to select the wrong answer. Okay, so consider the set of strings having all telephone numbers that have 3 digits. So 3 digits, then a hyphen, then 3 more, then a hyphen, and then 4 digits. So normally that regular expression would just be 3 digits, and then a hyphen, and then 4 digits, and so forth, except the first 3 digits have to either be an 800 or an 888. So it has to be one of the first 3 options, because only the first 3 options are the ones that require an 800 or an 888 at the beginning. Now, by the way, this is kind of an incorrect answer because by putting just parentheses, this is a capturing group. So this is actually assigning that result to a variable. It didn't say in the instructions to assign the result to a variable. So who remembers how to have a regular expression that does not assign the result of a group to a variable? How do you make a non-capturing group? With a question mark and a colon before it, right? So so technically this answer is not necessarily wrong, but it would have been better for them to put a question mark and a colon before the first 800 so that it would not capture that into a variable, because it didn't say to capture that match into a variable. Okay, so then now, but that's not the right answer though, because it says that it has to have the last 4 digits start and end with a 2. So it cannot be that answer. It has to be one of these 2 answers. So which of these answers is correct? Those are the only 2 possible answers that are right. The bottom one, and why is that? Yeah, but because yes, because the last one is correct, that the middle one is correct, because it says then it could be any digit from 0 through 9, and there's nothing in the instructions that says the last 4 digits can only be 1 through 9. So this says 0 through 9, it can be the last 4 digits, and that's correct. So it's that one. By the way, those brackets that say 3, that means that that thing before it has to happen exactly that many times. So when it says 0 through 9, 3, like that, that means that the digit 0 through 9 has to happen exactly 3 times in a row. You can also put 2 numbers, like if you wanted to say the 0 through 9 have to happen from 3 to 4 times, you could put 3 comma 4. That means it would match either 3 or 4 digits in a row. Okay, well then, final one of the review. So this is a finite state automaton A given the transition diagram below. So this is like how vending machines work, and actually this is also how regular expressions are also implemented a lot of times in like in assembly language or at the base level. So you're in a certain state, like somebody pushes a button on the vending machine, and if it's option 1, it goes to this state. If it's option 0, it goes to this state. And logical things that represented things like choosing pop and things like that, they had to be encoded in some form in binary to actually work with electronics before they had computers. So you had to design circuits that would move back and forth between different states. So what's the next state? If you start in state 1 and you choose option 1. Yep. So if you start in state 1 and you choose option 1, you'll end up with state 2. So state 2 is the answer. Now I forgot. Let me just check real quick. Do you have to put curly brackets around that? No, you don't. Okay. So you just say S2, that's all. Now, if you start in S2, which is that state, what if you start in S state 2 and you push the button number 1? What will happen? Yes. You'll get looped around and you'll come back to S2, right? Now, if you're in state 2 and you push option 0, so if you're in state number 2 and you push option 0, that'll be going from here out to there. You'll be in state 3, right? So if you're in state 2 and you push option 0, you'll be moved to state 3. And then if you're in state 3 and you push option 0, if you're in state 3, you push option 0, you'll be looped back into state 3. So that's cool. S3 again. Now, what's the next state? S in star means it accepts multiple button presses at once. 0, 0, 1, 1, 0 from state 0. So you're at state 0, and you do 0, 0, 1, 1, 0. So first you push 0, then you push 0 again, and then you push a 1, which moves you down here. Then you push 1 again, which loops you around, and then you push a 0, you'd end up at state 3, right? So let's double check, make sure I did that. 0, 0, 1, 1, 0, right? 0, 0, 1, 1, 0. Let's do it one more time. 0, 0, 1, 1, 0. So start at this state, move to 0, follow 0, then do a 1, then do a 1, and then do a 0. You'd end up at state 3. So it's like dot to dot, actually. So state 3. Now start at state 1 and do 10101. So no, sorry. Start at state 1 and do 10101. So state 1 and do 1, 0, 1, 0, 1. You'd end up at state 2, right? If I did that right. Yeah. So do you see how it works? So this is very abstract. It's not very hard, but it's just abstract. So now what's the next state star function of S2 of 01010? 01010. State 2, then 01010. We'll go to state 2, then do 01010. You'd end up at state 3, right? So you'd end up at state 3. State 3. And then start at state 0 and go 10110. So start at state 0 and go 10110. Start here and go 1, 0. I forgot what it said next. We're supposed to do 10110. So stay 0 and then 10110. 1, 0, 1, 1, and then 0. We'd end up with state 3, right? So the output of the final state would be state 3. So with that, I think we're all done with the review of the review. So once again, if you get every point possible on this practice review, like 3 other people have already done, then you don't need to take the final itself. If you don't, then you still might not have to take the final as long as the 10 people who are in the class that one day get an average of 90 or more. I'll let you know by this, like maybe Friday or Saturday, what the average is. If people don't get to that average though yet, then you'll have to do the first part of the final on next Monday, second part of the final next Wednesday, and third part of the final next Friday. And they'll be in class. And it'll still be based on this, but it'll just be on paper. Yes.
What is that like? What's the final day that we have?
Well, of course you have to finish the seminar before next Monday, because Monday will be when we'll have to start doing it. So, but whoever gets 100% on it, they don't have to worry about it though. Yeah.
Do we still get a grade for it?
Yeah, you'll still get a grade for it. So whatever grade you get. So if you get 100 on this, then you'll get 100 on the final.
Okay.
Yeah. Right.
And also,
And if you get it,
See if we submitted this, or do you want to, so I?
no, I can see that you submitted it through it. In fact, I just looked at the grades before I started class today. That's how come I know 3 people already got 100 on it. Yeah. All right. Good luck, everybody.
Thank you.
You're welcome.
Good day.
You too. Thank you very much. See you later.